Good day to you. Welcome to Can We Do That? Some more. The companion videos to the main Can We Do That series that we've got going on. These videos will always appear the Monday after the Friday that the Can We Do That videos appear. And they're basically just an excuse to do more maths. I like doing maths. It's not me just pretending that I like maths. I actually do like doing maths, and these videos are just an excuse for me to be trying out doing some questions rather than just explaining how you would approach them. The other advantage of them is because in the Can We Do That series we're looking at stuff that goes beyond the Maths A-level syllabus, you therefore don't have a bunch of questions readily available for you to try it in case you wanted to try doing some of the stuff, playing about with some of that stuff we're looking at in those videos. So these videos have the advantage of providing the opportunity to have a go at some questions if you so wish. And then, of course, these videos are giving you the work solutions to those problems as well. So it's a double whammy right there. So hopefully you find that enjoyable. Of course, being the first video, this is the companion to the further chain rule stuff that we're doing in the last video. However, before we continue on, a reminder that this stuff is just for fun. This is not stuff you need to be able to do for the Maths A-level exam or the Maths A-level exam for that matter. We're just doing this for fun. How many times can I say fun to make you convinced that this is definitely just doing maths for the hell of it? Anyway, last video, when we were looking at chain rule for higher derivatives, we came to the conclusion that you can do chain rule with higher derivatives, but instead of just multiplying the two derivatives together, you need this formula that's appearing on screen right now. If you want to know the proof behind that, then do look at that previous Can We Do That video, and there will be a link right now appearing on the screen, helping you take you to that video if you so wish. If you are having a go at these questions today, I would recommend you stop and write down this formula before we continue. I'm not going to make you derive it every single time. That would be painful. And I've also got it written down on a sheet of paper next to me. It's the only thing I've got written down already before the video, because I also will want to use this formula, several times throughout this video. Nice. Right then. Okay, with that said, here are the 4 questions that we are going to be trying. Again, at this point in time, you are welcome, more than welcome, to pause the video, and if you want to, have a go at these 4 questions. So do that, and when you come back, whenever that is, we're then going to have a go at actually doing the questions myself. I am going to have a go at doing the questions myself, and there you go. We'll see how that turns out. Brilliant. So let's get cracking. So the first problem, by the way, obviously I'm going to have, as you can see, the face cam to give this a more casual experience. The Can We Do That videos, I probably generally won't have the face cam just because that takes up valuable screen space for the many things I sometimes try to cram in on the screen on those videos. But these videos, by the way, are always going to be quite casual. They're always going to be done in one take. So things will probably go wrong at some point. I got the pressure of doing maths in front of an audience. That's always adds. I like the added danger. I like the added danger element to doing that. I'm used to it as a teacher ultimately, but it's a different thing doing it on a recording video because, well, my mistakes will be immortalized forever on the internet. But anyway, hopefully we won't make any mistakes. Let's see. So anyway, here's this first question. Basically just got to differentiate it twice. But we can, of course, use our formula to get there just the second derivative instantly. So, of course, as chain rule, you first decide your substitution, which we're going to just make the entire power of the substitution. That makes life a bit easier. You could choose to just make just sin x the substitution as well. Doesn't really matter, to be honest, which way around you do it. And then we are going to go ahead and actually differentiate both of these things twice. The e to the u bit, that's well easy to differentiate twice because it's just going to repeatedly differentiate to e to the u. One of the main reasons why e to the u or e to the power of x or e to the power of just, a single letter, no numbers, is always so lovely. Gradient the same as the y coordinate every single point. Anyway, 2 sine x, of course, sine will differentiate to a cos, and we're going to have that 2 out the front still. And then watch out, cos differentiates to a minus sign. So we got minus 2 sine of x. Brilliant. Now we've got all the pieces. We can now find what d2y over dx squared is. So according to the formula, that's d squared y over du squared, which is our e to the u, times by our du dx all squared. So that's 2 cos x all squared. And then we're adding on dy du, which is e to the u as well, times by d squared u over dx squared, which is our minus 2 sine x. Of course, I'm going to want to tidy that up and also undo the substitution. So if we're squaring the 2, we're going to end up with a 4 out the front. Lots of e to the u, and u is 2 sine x. And then we've got the cos squared x from squaring that out as well. And then tidying it up, the second bit, we've got a minus 2 e to the power of u, and u is 2 sine x. And then we've got that multiplied by sine x. There you go. So that's the second order derivative. If you wanted to, you could, of course, factorize bits of that out. You could even decide to replace the cos squared, so the entire thing's only in terms of sine, which would be useful if you're trying to find things to do with stuff. But anyway, there you go. That is, for all intents and purposes, it done. Nice. On to the second question. Weird thing is, you might know, the face cam disappeared for a second there. That's due, I think, the animations I'm using. Whatever. It's still all one take, believe me. Let's continue on. So again, we're going to do a substitution. Again, we're just trying to find that second derivative. So substitution, and write the original thing in terms of that substitution, and then differentiate both things twice. So that will become 3u to the power of minus 1, because that's what Lund differentiates to. D squared y over du squared will become minus 3u to the minus 2. And then differentiate the other thing, which is even easier to differentiate. So we've got, there we go, 10x to the 4, and then differentiating that again, we're going to have 40x to the power of 3. Yes, there you go. So now we've got all the component bits we need. We can now whack it into the formula. So therefore we have d squared y over that, so it's that thing, times by du over dx all squared. So it's that. And then we have plus dy du, which is 3u to the power minus 1. And then we're timesing that by the second derivative of u with respect to x. That's 40x cubed. Of course, now we're going to do some simplification after that. So we've got to be really careful here. We're squaring the 10 and squaring the x4. So the 10 squared is 100. And then timesing it by the minus 3 will get us minus 300. Wow. We've got an x to the 4 squared, so that gets us an x to the power of 8. And then we've got the u to the power minus 2. So actually I'm going to do the 2 stages. I'll write that u to the power minus 2 on the bottom for the moment. And then we're adding on 3 times by 40, which is 120. And we've got an x cubed. And then we're dividing that by u because it's u to the power minus 1. Nice. So therefore you could then choose to rewrite that as minus 300x to the power of 8 all over our u, which is 2x to the power of 5 plus 1, all squared. So all squared like that. And then we're adding on 120x cubed all over just our u. So 2x to the power of 5 plus 1. And there you go. Again, you may choose to factorize bits out of it. This question didn't ask you to do that, so I'm not going to. Effort. So there you go. That will do. It's fully simplified as much as I need to for the purposes of what we're trying to do. Nice. Let's go on to question 2. Now 2 is where we're going to start actually using stuff a bit more. Part A, actually quite easy. This is actually nothing to do with what we did in the previous video. It just wants you to find stationary points, which of course you should hopefully know is when dy dx is equal to 0. So you've got to find dy dx first of all using classic chain rule. Because I'm assuming chain rule is something a bit more, compared to the other stuff we're doing, quite chill, I'm kind of going to be a little naughty and skip a whole bunch of the steps and just tell you that dy dx, well, you just, differentiate the power like you normally would. So times by 2 to get an 8. 4 times by 2 is 8. And then reduce that power by 1. So we'll have the x squared minus 5x plus 6 to the power of 1. And then we're also going to be multiplying that by the derivative of the thing inside the brackets, the x squared minus 5x plus 6. And that is 2x minus 5. So there we go. That is what that differentiates to. Now we can do a bit of chain rule on that. We now will try and find the stationary points. That's when we set it equal to 0. So we've got this. Some people make the mistake of just unnecessarily multiplying things together. Sometimes don't. It's in factorized form, not fully factorized form, but partially factorized form. That's a good thing. If you're saying it equal to 0, you want things in factorized form because it means you can treat it as like mini equations. Because now we have 2x minus 5 is equal to 0 is one of the options. That, of course, leads to the x value of x equals 5 over 2. 2.5. Technically 2.5, but, mixed numbers suck, so we're not going to use them under any circumstances. And then, of course, the other option is x squared minus 5x plus 6 could equal 0 as well. And we solve that, and of course, it's a quadratic. So, if you can factorize it, which we can, because it's a nice example. It's a nice question. Which is not a coincidence. Although I haven't had a go at these questions yet, before making this video, I did it. I made these questions, so I do very least know whether it's going to work out nicely, vaguely or not. But anyway, therefore, we've got 3 stationary points. X equals 5 over 2, x equals 3, x equals 2. This one just wants the x coordinates of the stationary points. Always worth reminding you, exam technique back to A level. But if they ask for coordinates, then you do have to find y values as well. And if you're in 3D, not that you have to deal with that in maths A level, but university 3D, then you'd have to include those as well. So read the question carefully. There we go. Teacher hat on, teacher hat off. Right then, part B. Now we've got to determine the nature of those stationary points. So that's where the second order derivative comes in useful. Sometimes, a reminder that sometimes the second order derivative will come to 0, and then in which case you have no information, and therefore you need to use the gradient testing method by looking at the gradient either side of a stationary point to then determine what sort of stationary point you have. But we're going to use the second order derivative and hope that it works out. I say the word hope. I already know it's going to work out because I invented the question. Nice. So let's differentiate. Let's find the second order derivative. I am going to go back to the beginning again so I can use the formula. Saves me having to do more product rule and stuff like that. So we have u equals 4x squared. No, it doesn't. There we go. First mistake of the day. We knew it was going to happen. U equals x squared minus 5x plus 6. Tell you what, let's get rid of that horrible thing. Eraser. There you go. That worked out quite well, didn't it? Pen. Nice. Brilliant. That's u, and therefore y is equal to 4u squared. We can differentiate those things individually. 8u. We can differentiate again. And we're going to get 8. And we can differentiate this twice. So we get 2x minus 5. And we'll differentiate again. And we will get just 2. How very nice. Therefore, the second order derivative of y with respect to x is going to be d squared y over du squared, which is 8 times by du dx squared. So we have that. And then we're going to add on dy du times by d squared u over dx squared. Well, actually 8u times by 2, that's just going to be 16u. And of course we can simplify that. So it's 8 lots of 2x minus 5 all squared plus 16 lots of x squared minus 5x plus 6. Lovely stuff. Okay, nice. So that is the second order derivative, and therefore now we can use that to find what's going on at each of our stationary points from before. So of course x equals 2 is one of the stationary points. So now we find what dy of dx squared at x equals 2 is. And therefore we're plugging x equals 2 into there. Luckily that's going to come 0. And then we plug 2 into there. That means we're going to get 4. And 4 take away 5 is -1. -1 squared is +1. So it's +8. Oh, and that is greater than 0. So therefore, x equals 2 is a local minimum. Local minimum. Always remember it's the opposite way to how and that's why the pause. Always the opposite way to what I would want it to be. Positive is a minimum and negative is a maximum. Confusing, but there you go. At x equals 2.5, or 5 over 2, random switch the decimals halfway through for no reason. Then we plug 2.5 into there. Now 2.5, the left-hand bit is going to come 0, and we instead just got to plug 2.5 into there. I'm going to plug that into the calculator. I'm not going to do that in my head. I could, like any of us could, but it doesn't mean I want to. It hurt my head, hurt my brain. So let's type it in. Proof that I'm doing it live because I'm actually manually typing it in as we speak. So you get that, and then we times it by 16. -4. -4. And oh my goodness, -4 is less than 0. Therefore, x equals 5 over 2 is a local maximum. Cool stuff. Let's do x equals 3. You might already be able to guess how this is going to go. And partly, I mean, you know, I didn't bother multiplying the brackets for this one. You could have. That would be another way of avoiding chain rule completely. But that would be a lot of multiplying out brackets, squared by squared. And that's why actually this arguably is quicker. Certainly it'd be quicker if it's power 3 and above. But anyway, plug in x equals 3. The right-hand bit will now be 0. And therefore plug 3 into just that bit. You get 6. 6 take away 5 is 1. 1 squared is 1. It's 8. There you go. So it's 8. And oh my goodness, 8 is bigger than 0. And therefore x equals 3 is a local minimum. Nice. If I'd been prepared, I would have showed you on Desmos what that looked like as a graph. But I haven't. But anyway, so Cortex, you know, it's a sort of terrible drawing up here. There we go. It's going to be that sort of graph. So hence why minimum, maximum, minimum sort of scenario with our stationary points. It makes sense. It's not entirely surprising. Positive Cortex shell, I should also clarify. Anyway, there you go. That's question 2 done. Let's have a go at question 3. Find the x-coordinates of all the points of inflection. Oh my goodness. And to find points of inflection, we need the second order derivative. What a surprise. So, let's pick our substitution, which is going to be obviously the stuff that's inside the brackets. And then, of course, we have y equals u to the power 5 as the original thing in terms of the substitution. Differentiate that twice. 5u to the 4. And then, oops, not x. There you go. Corrects my. That was just a note. That wasn't a proper mistake. That was just a notation mistake. Still should correct it. Notation is important. So many students don't bother with notation, and they wonder why. Then they don't understand what's going on. It all just looks like a bunch of random letters on a page. But the notation is telling you stuff. It matters. So there you go. I'm differentiating the other thing a couple of times. You'll get that, I hope, I believe. Nice. So now we can use all that stuff to find the second order derivative. I'm going to cram that up here. Why not? Therefore, that's going to be d squared y of du squared, 20. See, I don't know the formula that well. 3x squared minus 16 all squared plus, what else do we have? We've got dy du, which is 5u to the 4. And then we've got d squared u dx squared, which is a 6x. Nice. So what you can do is you can then start to gather that all together. Replace the u's, all that sort of stuff. If you were to do that, let's move ourselves down here. We're going to end up with d squared y over dx squared equaling, my goodness, I'm going to have fun fitting this into the page, 20 lots of x cubed minus 16x all to the power of 3 times by 3x squared minus 16 squared plus, we got the 5 times the 6 is a 30. I'll gather the x out the front. And then we've got x cubed minus 16x all to the power of 4. Okay, we can then factorize that, because we know we're going to, in order to find not stationary points, the points of inflection, we're going to need to set this equal to 0. Therefore, factorized form would be helpful to make our lives easier. Some people make the mistake again of just multiplying all the brackets out here. If you do, you get the correct answer eventually, but you end up with a horrible polynomial that you might not know how to solve, etc., etc. I don't know. I haven't tried multiplying that out, but that's the point. I'm not going to waste the time. So what we're going to do is going to factorize out common factors. Obviously, you can factorize at 10 out of everything there. That makes stuff a lot nicer for a start. We can factorize out x cubed minus 16x all cubed out of the entire thing. Brilliant. So that will leave us with 2 lots of 3x squared minus 16 all squared. And then add on 30. Not 30, no, just 3. And x, and just 1 lot of x cubed minus 16x. Okay, and then we can do some more simplifying, can't we? So let's do that. 16x. So we still, no escape from multiplying out brackets. It's just less brackets than we otherwise have. So, therefore, we're going to have to fully multiply out those brackets. So that's going to be a 9x to the power of 4. 3x squared times by 16 is 48. X squared, double it, because it's the square bracket. So it's minus 48 times 2 is 96. X squared. And then plus 16 squared is 256. Wow, big numbers. And then we're having 3x to the 4, and we got minus 48x squared. Right then, we've run out of room on this slide, so we're going to have to flip over to the next slide. Oh my goodness, the trouble is I now got to flip back and forth to see what's going on. Okay, so the 10, apologies. See, I was slightly prepared though. I had a feeling that I'd probably need another slide to do this. So I did leave room for this extra slide before the next question. I won't call it a genius move, that's going a bit too far, but it's something. It's some sign of forethought into these videos. Oops, wrong direction, wow. 18, 192. And 256 times by 2, which is 512. And then we're adding on the other two things. Oh my goodness, the wrong way again. One day I'll learn. Plus 3 minus 48. Plus 3 x to the 4 minus 48 x squared? I can't remember. Was it x squared? It was an x squared. There you go. I can remember stuff sometimes. Then simplifying that. We're putting the effort in now so that it's then easy to solve in a bit. So this seems like a bit of a chore now. But that is 21x to the 4. That is another 48. So that's minus 240 x squared. And then lastly, plus 512. Okay, if we're looking for points of inflection, if they are going to occur anywhere, they're going to occur when the second order derivative with y respect to x is equal to 0. But worth reminding, that isn't enough to say it's a point of inflection. But it's a good starting point. You know a point of inflection won't happen anywhere else other than these points. So we're at least narrowing it down to what points we have to look for. So with that said, let us now solve that. So there's two mini equations we can solve there. There's x cubed minus 16x all cubed equals to 0. Of course, that's a quite nice equation because it's the same as just doing x cubed minus 16x equals 0. We don't really care about the fact the cubed or cube root both sides the other way of looking at that. And then also we can factorize that. So that's x, lots of x squared minus 16. And that can be factorized some more. So then we're going to have x x minus 4, x plus 4, using difference of two squares, of course. So x equals 0, 4 or minus 4 are three only potential at this stage, points of inflection. And then the other mini equation to solve is effectively a disguised quadratic. It's 240x squared plus 512 equals 0. You could choose to simplify that quadratic if you want. I'm just going to be using the calculator to help me do it, because I'm just going to use the quadratic formula. So I'm not going to show the working for that. Terrible, I know. But I'm hoping if people are doing second order chain rule, solving a quadratic should be the least of our worries. So if we solve that, wow, okay, these are not quite so much nice numbers. That was terrible English as well. Apparently, this is x squared will equal 120 plus 8 root, so technically plus or minus 8 root, 8 lots of root 57, all over 21. So there you go, we've got a quadratic, and if we can square root that to get what x is also equal to, x is either equal to the square root, can we square root them? I don't think they're going to square root nicely, but we should check. I almost guarantee they're not going to square root nicely, but we should check. We got the calculator, why not? Why not? Shock horror, they do not square root nicely, or at least the calculator just can't do it for me. So we'll just write it in exact form. I've got the decimals as well. I'll write them actually below it. It's 2.93 to 3 significant figures, right? 2.931 to 4 significant figures. And then the other one, of course, is the negative. Oh my goodness, no. Wow. Okay, there's a lot of points we're going to have to check here, because we're going to have to check. Let's actually double check, first of all. Because we're going to have the plus and minus versions from the quadratic formula. Oh, wow, we are. Okay, so we're going to have 4 extra solutions to look at. So minus 8 root 57 all over 21. And then we've got the plus versions of them. Let's have a look at all that. That's 1.685, 1.685. And, of course, we've also got minus root 120 plus 8 root 57 all over to 21, which of course is minus 2.931, and then we've also got minus root 120. Sorry, my handwriting's going to pot here. Doesn't really matter. Equals, so that's minus 1.685 to 4 significant figures. Right then, so we've got potentially 7, my goodness, 7 stationary points, not stationary points, points of inflection to check. To check for their points of inflection, all you got to do is check the sign of the second order derivative either side of it. So that is what we're going to do now. What you're looking for is a change of sign either side of each of them to see if they are a point of inflection. Luckily, there are no what's called discontinuities, which is a posh way of saying vertical asymptotes to be watching out for. There are no further, there's no points where the gradient is vertical or anything like that. So basically, we can just pick any point in between these not stationary points, keep them calling them that, potential points of inflection. So therefore, we'll do it all in a table, all in one big go, because we can also just start to choose to pick nice numbers. So x equals, what's the smallest one here? Minus 4. And then, of course, we already know, wait a minute, sorry. Got to pick a point to the left of minus 4 first. So minus 5. We already know minus 4 will come to 0. We'll then pick a point that's to the right of minus 4, but before the next station point, which is minus 2.9. So we could pick minus 3. Conveniently, just about that would work. We got minus 2. I'm just going to write, you know which one that's talking about. Therefore, we've got the minus 1.68. So minus 2 will work in between that. We know that's another one where it's 0. We could pick -1 because that's before the next one of 0. Then we pick 1. And then we'll also have some more for another row. Wow. This really was a mega question, Greg. Why did I pick such a crazy question? I'm not sure. My goodness, I don't have room. That says, let's just pretend that says d squared y over dx squared. It won't let me fill that in. But basically just continuing on up. Oh, my goodness. The joys of doing this live. 1.68, etc., etc. We know that's where there's another thing. 2, and then we could 2.9 is where another one was. We know that's where it's 0. 3, and we know where 4 is another one, and then 5. So we're going to check all of these, plugging them into our second order derivative. Don't worry, I'm going to do this quickly, all using still the calculator, but there's a function on the calculator that lets you plug in multiple values of something all at once, often called the table function. That's what you want to look out for. Lets you put in a function and then tell it what several x values you want to plug in all at once, and it just lets you do it, which is quite good. We like that. We like that a lot, particularly right now. Imagine if I had to manually type in all however many points that is. It's a lot of points, and I don't want to do that. I do not want to do that at all. So let's double check I've done that correctly. Power 3, power 4, 2, there we go. Correct coefficients. Yeah, okay, so we're going from -5 all the way to 5, and we're doing every 1. Cool. It's taking a bit of time there for thinking about it. Okay, wow, okay. Let's just say that's a really big negative number. It's -6 times 10 to the power of 9. Probably can't even see that, but basically the point is it's a negative number. And then we have 4.9 to the power of times 10 to the power of 6. Nice. And then we have 9.8 to the times 10 to the power of 6. Again, I've rounded all these values, or truncated them. They're truncated, even worse. It's because I'm not bothered about that's terrible maths, but we're not bothered about this specific number. We just want to know whether they're negative or not. -9 times 10 to the power of 6. And then -49, -4 times 10 to the power of 6. Let's say if we're truncating that. Wait a minute, sorry, that was meant to be 0, that one there, wasn't it? It's 1. 1 we're looking at now. Oh my goodness, no it isn't. I've missed so many out. Go back. Sorry, I've told you lies. Eraser. Wow. Goodness me, not having a good day here, am I? But as I said earlier, at least it proves that I'm doing it live, because it's, suitably chaotic. So that was 4.9 times 10 to the 6. I'll just write 4 times 10 to the 6. Let's truncate even more. -2 is -1 times 10 to the power of 7. We want -1, that's 9.8 times 10 to the power of 6. 1, which is -9 times 10 to the power of 6. That's 10 to the power of 6 as well. My goodness, you can't even see it. Dreadful. Shoddily made video. 1.5 times 10 to the power of 7. -4 times by 10 to the power of 6. And lastly, 6.9 times 10 to the power of 9. What conclusion can we make? Well, if we're looking for points of inflection, you're looking for there being a change of sign either side of the point where the second order derivative is 0. So at -4, we can see it's minus before and positive after. Therefore, the points of inflection, if we're listing them, points of inflection, x equals -4. We can see there's a change of sign about 2.9. So my goodness me, I'm going to have to write out that awful thing. So let's do that. Let's do that indeed. In fact, actually, looking at this, okay, interesting. They're all points of inflection. Wow. Wow, they all are. They all are. I'm not going to bother writing them out again because it turns out they all are. There you go. I should have seen that coming. It makes sense. It's what sort of graph did we originally have? Let's have a look. I've forgotten. We originally had an x to the power 5 graph. No, x to the power 15 graph. Okay, wow. So it's an odd function. Actually, is it an odd function? Depends on symmetry. Basically, goes up forever on the right, goes down forever on the left. But yeah, there we go. A lot of points of inflection there. Amazing. Not particularly nice numbers. I hope I got that right. I'll check after the video. If they're not right, then suddenly this bit will just weirdly get cut out for no reason. Anyway, last question. Some of you are looking at this. Why is it? Yeah, it is question 3. It should be question 4, I'm pretty sure. Never mind. Anyway, find the third order derivatives. Some of you looking at this going, Greg, why are we doing this in this video? Because surely you already showed this in the other video. Well, it's because I know a few people would have been looking at this, us finding this in the previous video and thinking, why didn't, even if we were, instead of using Faraday-Bruno's formula, even if we were finding it manually, why didn't you use Leibniz's theorem for higher derivatives, which is a topic within FP1 of further maths. There will be a video on that at some point on the channel, not yet. Why didn't I use that to quickly differentiate it twice rather than manually differentiating using product rule 50 billion times? And well, the answer is because we'd already found the second order one, it was quicker to just jump to that from it. So, but anyway, from this video, I can get to show you the other way. So everybody's a winner. So, therefore, a reminder that dy dx is equal to dy over du times by du over dx. And what I'm effectively going to do is I'm going to do Leibniz's theorem to differentiate this twice to get the third derivative. Just so using Leibniz will allow me to differentiate this twice very quickly. So, I say that, you'll see actually why I didn't do this in the original thing. It isn't really that much quicker. But some of you might be interested. So here we go. Here's me doing it using Leibniz's theorem. So we have A, which is going to be dy over du, and then we differentiate that twice. That is why this is a problem, because you'll quite quickly see that takes a lot of effort to differentiate. dA over dx is therefore equal to d squared y over du squared times by d over dx. That's something we covered a lot in the original Can We Do That video for this stuff, for chain rule, implicit differentiation. That's what's going on. You look at the letter that's on the bottom, basically, that's the letter you're differentiating. We're meant to be differentiating x's though, so that's why I do the implicit differentiation correction. The painful part, though, is we're then going to have to do product rule within Leibniz's theorem in order to do this, because, you know, this didn't work out nicely. So we're going to have to do product rule with that. So therefore, we're going to differentiate the first thing while keeping the second thing the same. So that'll end up getting you d3y over du cubed times by du over dx. And then we're going to times that by du over dx, because that's the other thing not differentiated. Then doing that the other way around, not differentiating d2y over du squared, but instead differentiating du dx, which is d squared u over dx squared. Of course, you can simplify this a bit. Do du over dx all squared plus d squared y over du squared, d squared u over dx squared. So that's the first bit dealt with. And then we're going to take our b and differentiate that a bunch of times. So I'm going to have b equals, what is my b? My b would be d over dx. Actually, this is the nicer one. This is the nicer one to differentiate. So db over dx. Some of you are wondering why I'm writing it in this weird way. It's because it makes the derivatives that need to multiply by each other line up nicely. But anyway, this is nice and easy. They just go to higher derivatives for the second one. Not much thought required, which I like. d3u over dx cubed. Last part of Leibniz's theorem for higher derivatives is using the NCR, binomial coefficients, to multiply these things. So of course this thing and this thing will get multiplied by 1, and this thing in the middle, combination in the middle, gets multiplied by 2. So with all of that said, we can now go ahead and do Leibniz's theorem. So we're going to have everything over here multiplied together. So if we were to multiply those things together, we'd have du over dx times by this stuff, which means we're going to have an extra du over dx. That means we're going to have du over dx all cubed. So let's write that down. We're going to have d3y over du cubed times by du over dx all cubed. And we're going to then be also timesing du over dx by this thing, which is going to have plus d2y over du squared times by du over dx times by d squared u over dx squared. I think I wrote that down correctly. We've also then got this all multiplied together, so we got 2 lots of that thing, which is interesting because you'll see that's why we end up with 3 lots of it overall, confirming what we got in the previous video. And then lastly, we're going to add on all this stuff multiplied together. So that gets us dy over du times the third derivative of u with respect to x. Cool. Of course, you'll obviously spot in the middle, we can do some simplification. So that does lead to us confirming the answer we got in the previous video, which is d3y over du cubed times by du over dx cubed plus 3 lots of d squared y over du squared du dx d squared u over dx squared, and then lastly dy over du times by d cubed u over dx cubed. There you go. So that is the same as what we got in the last video. I'm saying that I can't actually remember if it is, but that does look roughly the same as what we had last video. I'm going to assume I'm right. And therefore, we're done. Hooray. There you go. All 4 questions done. That's full work solutions to all of them. Hopefully, that linked up with what you got as well. If I've made any mistakes in the final answer, please do point out those mistakes in case I didn't spot any of my own mistakes. And I'm not offended by that if you do that. And therefore, that will do us for today's video. That is, can we do that some more? And we'll be doing that for not all the Can We Do That videos, because some of them, as you'll see when those topics appear, it won't make sense to have another video doing some more stuff with them. But whenever it makes sense to, I will be doing one of these videos afterwards. On the screen right now, you should see a link to the next video in the Can We Do That series. Obviously, if you're watching this video right now on the day it comes out, the next video in the series is not out yet, but it will be. It will be eventually. And then also there is a link to a video in my Prove It series. I'd always encourage you to also watch that video if you're interested in maths. We look at proving loads of stuff in the Maths A-Level syllabus. And that's really cool. That's really cool. So I would recommend doing that. It's also another fun series. And lastly, also, do subscribe to the channel, like, comment, all those sort of things. Show support. Because if you do, I'll do more of these videos. Who am I kidding? I'm going to do more of these videos anyway, but still, it means a lot if you do support the channel. Right then, adios.